You think space and time are different things. Space is where things happen, time is when they happen. Space is out there, around you, between objects. Time is what flows forward second by second. These feel like completely different categories of reality, except they're not. Space and time are the same thing, not similar, not related, the same. The different aspects of a single, unified entity called space-time. And once you understand this, your entire sense of reality has to change. I'm Leonard Susskind, and the unity of space and time is not a metaphor, it's what the universe actually is. Let me start with what you think you know. You think you're sitting still right now, not moving, and in one sense that's true, you're not moving through space. But here's what Einstein showed. You are moving right now at incredible speed. You're moving through time at exactly 1 second per second. And that motion through time is fundamentally the same kind of motion as moving through space. You have a velocity through space-time, a four-dimensional velocity, and the faster you move through space, the slower you move through time. The two are linked, they trade off, and the total velocity through space-time is always exactly the speed of light. You are moving through space-time at the speed of light right now. You're just moving almost entirely through the time dimension. When you start moving through space, you redirect some of your motion from time into space. And because your total velocity is fixed, when you move faster through space, you move slower through time. This is time dilation, real, measured, confirmed, thousands of times. Now, I know what you're thinking. That's just a mathematical trick. You're treating time like a fourth dimension. But that doesn't mean space and time are actually the same thing. And that's where you're wrong. The mathematics isn't a trick, it's a description of reality. Space and time really do form a unified four-dimensional structure, and the evidence is overwhelming. Let me give you the simplest proof. The speed of light is constant, 300,000 kilometers per second. Every observer measures light traveling at exactly that speed regardless of their own motion. This is the foundational fact of special relativity, and it seems impossible. If I'm standing still and you're running toward a beam of light, shouldn't you measure the light going faster? No. You measure exactly the same speed. The only way this can work is if space and time are not separate. They have to trade off. When you move faster through space, distances in the direction of your motion contract, and time slows down. These effects are calibrated so that you always measure the same speed of light. But here's what this really means. What you call space and what you call time depend on your motion. Events that are simultaneous for me are not simultaneous for you if you're moving. Distances that have one length in my reference frame have a different length in yours. Space and time are not absolute. They're relative. And if space and time were truly different kinds of things, this wouldn't be possible. The fact that motion through space affects the passage of time proves that space and time are made of the same fundamental stuff. They're dimensions of a single continuum, space-time. Let me make this concrete. Imagine two events. You clap your hands, 1 second later, you clap again. In your reference frame, these events happen at the same location in space, but separated by 1 second in time. Now imagine I'm in a spaceship flying past at high speed. From my frame, those two claps happen at different locations in space and separated by a different amount of time. The interval has both a spatial and temporal component, and the mix depends on velocity. But there's a quantity called the space-time interval that both of us agree on. It's calculated using both spatial and temporal separation, and it's the same in every reference frame. This space-time interval is the real physical distance between events in four-dimensional space-time. What varies is how that interval gets divided into space and time. This is exactly analogous to space itself. Imagine a stick lying on a table. The stick has a length. Now you come in from a different angle. From your perspective, the stick is oriented differently. Part of its length points east-west and part points north-south. We disagree about how much is east-west, but we agree on the total length. We're just measuring from different orientations. Space-time works the same way. The space-time interval is like the length of the stick. Different observers decompose it into space and time differently, but the underlying four-dimensional interval is the same. Space and time are directions in space-time. Now, let me talk about why this is so hard to accept. We move very slowly through space compared to the speed of light. Even airplanes only go about 0.0001% of the speed of light. At such slow speeds, time dilation and length contraction are tiny, unmeasurable in everyday life. So our intuition developed in a regime where space and time seem separate. We never experience mixing. Time always seems to flow at the same rate, but that's an illusion. When you move at a significant fraction of light speed, the mixing becomes obvious. Physicists have measured this directly. We put atomic clocks on airplanes flying around the world. When they return, they're behind the clocks that stayed on the ground. The moving clocks experience less time. The effect is tiny, nanoseconds, but it's real, and it matches Einstein's predictions exactly. We've also measured length contraction indirectly. Particles created in the upper atmosphere by cosmic rays are unstable. They decay in microseconds. They shouldn't make it to the ground, but they do. Why? Because from the particle's perspective, the atmosphere is length contracted, the distance is shorter. From our perspective, the particle's time is dilated, it lives longer. Both perspectives are correct, and both show space and time mixing. Now, the mathematics. In three-dimensional space, distance squared equals x squared plus y squared plus z squared. In four-dimensional space-time, interval squared equals x squared plus y squared plus z squared minus c squared t squared. Notice the minus sign. That minus sign is everything. It tells you time is different from space and sign. Space dimensions contribute positively, time contributes negatively. This allows time to trade off against space. This mathematical structure means space-time is not just four-dimensional Euclidean space. It's a Lorentzian manifold. The geometry is different. In ordinary space, you can rotate, turn east into north. In space-time, you can also rotate, but these rotations mix space and time. They're called Lorentz boosts, and they correspond to changing velocity. When you accelerate, you're rotating in space-time. You're changing the angle at which your world line points through time and space dimensions, and this rotation mixes them. What was purely time becomes a mix. Every object has a world line in space-time. Your world line is the path you trace through the four-dimensional continuum. If you're sitting still, your world line points purely in the time direction. If you start moving, your world line tilts. It has components in both time and space. Light has a special property. Light moves through space-time at a 45-degree angle, equal amounts of space and time. That's why light has a finite speed. Massive objects can never reach that tilt. Their world lines always point more toward time. This is why you can never reach the speed of light. It's a geometric fact about space-time. Now I want to talk about simultaneity, because this is where unity becomes most obvious. Simultaneity is the idea that two events happen at the same time. In everyday experience, simultaneity seems absolute, but that's wrong. Simultaneity is relative. Here's a thought experiment. I'm standing on a train platform. A train rushes past at high speed. Exactly when the middle passes me, lightning strikes both ends simultaneously from my perspective. I'm equidistant. The light from both strikes reaches me at the same time, so I conclude the strikes were simultaneous. But ask someone on the train. They're moving toward the front strike location and away from the back. The light from the front reaches them first. So they conclude the front strike happened before the back strike. Who's right? Both. There is no absolute simultaneity. Events that are simultaneous in one frame are not in another. And this isn't about signal delays. This is about space-time structure. Different observers slice space-time into space and time differently. My slice of constant time is different from the train observer's slice. We disagree about what now means. This only makes sense if space and time are part of the same structure. If time were absolute, simultaneity would be absolute. But there isn't. There's only space-time. And different observers cut it along different angles. Let me make this dramatic. Imagine Alice is in a spaceship traveling toward Andromeda at 90% of light speed. What does Alice's now mean? Because of her high velocity, her surface of simultaneity is tilted relative to Earth's. Events in Andromeda that I consider to be in the future by hundreds of years are happening right now, according to Alice. If she turns around, her now slice tilts the other way. Events hundreds of years in my past are now according to her. Alice didn't do anything to Andromeda. She just changed velocity. She rotated in space-time, and that rotation changed which events she considers simultaneous. This is only possible because space and time are unified. Her rotation mixes them. Now let me address a confusion. Some people think space and time being the same means they're interchangeable, that you can travel backward in time like you move backward in space. That's not right. They're the same kind of thing. Dimensions of space-time, but they're not identical. The minus sign in the metric gives time a different character. Time has a direction, an arrow, entropy increases, causes precede effects. You remember the past but not the future. Space doesn't have this directionality. You can move freely in any spatial direction, but in time, you can only move forward. This asymmetry is important. Space and time are unified in space-time, but they're not perfectly symmetric. However, the arrow of time is not a feature of space-time geometry itself. It's a feature of thermodynamics. At the level of space-time structure, time is just another dimension. The arrow comes from initial conditions. Let me talk about general relativity, because this is where unity becomes even more profound. In special relativity, space-time is flat. But in general relativity, space-time is curved. And the curvature is caused by mass and energy. Matter tells space-time how to curve, and curvature tells matter how to move. In general relativity, gravity is not a force. It's the curvature of space-time. When you drop a ball, it's following a straight line through curved space-time. A geodesic, the ball is in free fall, but because space-time is curved by Earth's mass, the geodesic appears as a curved path. The ball falls. And curvature mixes space and time thoroughly. Near a massive object, time runs slower than far away. This is gravitational time dilation. GPS satellites have to correct for this. Their clocks run faster than clocks on the ground because they're farther from Earth's gravitational field. About 38 microseconds per day. If you don't correct for it, GPS wouldn't work. This time dilation is a spatial effect. Time runs at different rates at different locations. The flow of time depends on where you are. Space and time are so thoroughly mixed that you can't separate them. Near a black hole, this becomes extreme. As you approach the event horizon, time dilation becomes infinite from a distant observer's perspective. Your clock appears to stop. But from your perspective, you cross infinite time. Inside the horizon, the roles actually swap. The direction toward the singularity becomes time-like. You can't avoid moving toward it any more than you can avoid moving forward in time. This is the ultimate demonstration that space and time are not separate. Their roles can interchange depending on curvature. What is space-like in one region can become time-like in another. The distinction is not fundamental. What's fundamental is space-time. Let me give you a practical example. Particle accelerators. At CERN, protons are accelerated to 99.9999% of light speed. At these speeds, time dilation is enormous. From the lab's perspective, protons circle about 11,000 times per second, but from the proton's perspective, time is dilated by a factor of about 7,000. And distances are contracted by the same factor. The ring is much smaller. These effects are not small corrections. They're essential. If you ignored relativity, the calculations would be wrong. The protons would smash into walls. But when you account for space-time, everything works. Space-time is real. Now let me talk about why this is philosophically important. For thousands of years, humans believed in absolute space and absolute time. Newton formalized this. Space is a fixed stage. Time is a universal clock. Space and time are separate, independent, absolute. And for 2 centuries, it worked. It predicted planetary orbits. It seemed correct, but it was wrong. Einstein showed that space and time are not absolute. They're not separate. They're a unified 4-dimensional structure that responds to matter and energy. That gets curved. That mixes space and time depending on motion and gravity. Newton's picture was an approximation, good enough at low speeds, but fundamentally incorrect. This was a revolution, one of the deepest shifts in human understanding, and most people still haven't absorbed it. They still think in Newtonian terms, separate space, separate time. But that's not how the universe works. The universe is space-time. Let me give you one more piece of evidence. Light. Light doesn't experience time. From a photon's perspective, the moment it's emitted and absorbed are the same moment. No time passes. This is because light moves along null geodesics in space-time, paths where the space-time interval is 0. For light, space and time cancel out exactly. Space and time merge completely. And light is the mediator of the electromagnetic force. Every time you see something, every time you touch something, all involves photons. The entire material world is held together by particles that don't experience time. Particles for which space and time are unified in the most extreme way. This tells us that space-time unity is fundamental. Let me bring this back to you. Right now, you're moving through space-time. Your world line is tracing a path through the 4-dimensional continuum, mostly through time, but also through space as Earth rotates. As it orbits the sun, your world line is a complicated curve. Every choice you make, you're altering your world line. You're changing the angle at which you cut through space-time. And because space and time are unified, when you change your motion through space, you change your motion through time. You age at a different rate. The effect is tiny for normal speeds, but it's real. Astronauts on the International Space Station age slightly less than people on the ground. You are a 4-dimensional object. Your world line extends from birth to death, a continuous thread through space-time. The you sitting here now is one cross-section, and past you and future you are other cross-sections. They all exist in the space-time structure. This is the block universe view, and it follows directly from the unity of space and time. Could this all be wrong? Could future discoveries show that space and time are separate? Extremely unlikely. Special relativity has been tested to absurd precision. GPS wouldn't work. Particle accelerators wouldn't work. Electronics relies on relativistic quantum mechanics. Space-time is confirmed reality. General relativity is equally well tested. Gravitational time dilation, gravitational waves, black holes. Every test shows that space-time is real. You might wonder about quantum mechanics. Does it change the picture? At very small scales, does space-time break down? Maybe. At the Planck length, quantum effects might become important. We don't have a complete theory yet. String theory, loop quantum gravity are attempts. But even if space-time is emergent, It's still real at the scales we can measure. The unity of space and time is not a mathematical convenience, it's a description of reality. Space and time are directions in a four-dimensional continuum. How you decompose that continuum depends on your motion. There is no absolute space, no absolute time, no universal now. There's only space-time. This should change how you think about the universe. You're not moving through space and separately through time. You're moving through space-time. That motion is a single, unified thing. The universe is not a three-dimensional space that evolves. It's a four-dimensional space-time, past, present, future, all existing as part of the structure. I've spent 50 years working with space-time. The unity of space and time is one of the most beautiful truths physics has revealed. It's counterintuitive, hard to accept, but it's correct. Space and time are the same thing, different aspects of space-time. And once you really understand that, you see the universe in a completely different way.